simulations, he thinks it's possible that the Earth actually stole other planets or other solar systems, comets. So, because you can do this simulation, and they start forming a structure, jets start forming a region, and then you send some Margaret away, and things look right. So perhaps our work about, for example, really from some other.
Oh, that's really cool. Slowly. That's really neat.
Yeah.
Oh, what is that weird solution? Wow, got it. Excellent.
That's like over a
Free presentation.
How do you make a presentation about September? This is so cool, right? That's cool.
It's just it's both exciting and scary.
Yeah.
It's so far away.
Yeah, I'm going to continue doing this. We actually have data. Yeah.
I have a one. I've been to Oregon.
Oh.
Because I love students and I was in Oregon. You were at M&A, yeah. A hot day when there was nothing happening and I was really sitting on it. And I was kind of close. Like,
So let's get started, please, everyone. Welcome to the second seminar. Okay, Alicia, that's enough. Come on, listen. No, you gave your seminar already. All right, too much coffee. So welcome to the second seminar of the 2015-2016 DTM seminar series. I'm pleased to introduce our speaker, Dr. Hal Levison from the Southwest Research Institute in Boulder, Colorado. Hal did his undergraduate research or his undergraduate degree and maybe some research too up at Franklin Marshall College just north of us. Then he went to the University of Michigan to do a Ph.D. and a master's with Doug Rich, still working on galaxies of all things, galaxy dynamics. As a result of which he followed that up with going to a NASA Ames postdoc, not to work on planet formations and chondrules like many of our postdocs have in the past, but to work with Bruce Smith and Dick Miller on galaxy dynamics again. So he was turning into, or he was an extragalactic, shall we say, astronomer at that point. Yeah. But then he went to work for the Naval Observatory, first the Flagstaff Station and then here in Washington, D.C., and realized that planets were kind of interesting. And so we won him over by a force of the excitement of our field. And after
Interpersonalities. It's actually true.
And so he was in the orbital mechanics department, which is a nicely named. You can just imagine them there with their screwdrivers and wrenches and things putting it together. And after the Naval Observatory, he went to Southwest Research Institute in Boulder, where he's been ever since, I believe.
San Antonio for 2 years.
Oh, sorry, San Antonio, which is still Southwest.
It's Southwest, yes.
From San Antonio branch, then on to Boulder, which was, I guess, created by Alan Stern. He was the one that...
Well, he and I started it together.
Okay.
We were 2 people, and now we're almost 100.
Okay, I'll give you equal credit with founding.
Yeah. Well, don't give me equal credit.
And I also want to point out that...
That's always a mistake.
Hal also co-authored the Swift code with Martin Duncan. One of the first symplectic integrator codes was generally available. I downloaded it one day back in a year or two after it came out in what was 86, 85?
No, 93.
93,
but
okay.
That's still a long time ago.
But
There's probably postdocs here that were born after that.
The cool thing was I downloaded it, and by the end of the day I had a simulation running for stability of planetary systems, and those simulations actually led to the only paper that George Weatherall and John Chambers and I, the 3 of us, co-authored. So they helped bring us together, Hal. So thank you very much. Today he's going to tell us about Pebble accretion. Take it away.
Well, thanks for inviting me. I've never been here, and I've always been curious. So I really appreciate you inviting me. Well, let me go back. Didn't mean to do that. So I'm going to present to you what I think has the potential, at least, to really be a revolution in our understanding about how planets form. And that's the role of pebbles in the accretion of planets. Essentially, I'm going to argue that objects the size of Mars essentially formed entirely by accreting things about the size of that bomb. Okay? The work that I'm going to present that I've done has been in collaboration with these guys, but as I'll show you in a minute, here's an outline of my talk. most of what I'm going to talk about today is other people's work. And I'm just going to throw my stuff in the end. What I've been doing in this game is really not coming up with any of the ideas, but taking the ideas of other people and throwing it into big n-body calculations and seeing if whether they're saying actually works or not. And they've been about 50-50, working and not working, as I'll show. So the outline is I'm going to spend about 10 minutes talking about the classic theory of planet formation, just to make sure we're all on the same page. There's some concepts that I need to present that are going to be important when I start talking about Pebble accretion. Then I'm going to talk about problems with the standard model, give you a review of Pebble accretion, again, it's other people's work, that's in the literature, and then move on and talk about what we've been doing, putting these things in the big n-body codes and what works and what doesn't. So let me start off with this, what I call the classical picture of planet formations, the 6.5 steps rather than 12 steps. Okay, basically, as you all know, the planets formed from a disk that formed as the sun was collapsing in order for the sun to shed its angular momentum. And then there's a story, the story is mainly a story, I should say, of just two-body accretion, right? Things coming together and sticking. And that's happened in various different ways at different stages. First, early on, you had dust in the disk. The dust hit at very low velocities and stuck until we get to a point of something like 1 kilometer or 100 meters or so, where gravity starts to become important. And I'll talk about the problems with these ideas in a minute. I'm just sort of giving you what the standard picture is, or was. Once you get things that we would call planetesimals, right, they grow in various stages. The first stage is runaway growth, where a few guys that just happen to be lucky to be a little bit bigger grew faster than everything else and sort of became the planetary embryos of which the planets formed. They run away because not only, if you look at this little equation, and by the way, this is about as complicated as my equations get, okay, in this talk, right, is the mass accretion rate scales as the cross-section, but it's not just the physical cross-section you need to worry about here. Here's an object, but it's also has to include what we call gravitational focusing as two things approaches, right? They follow Kepler orbit, and so rather than just accreting from that little, my mouse isn't doing a very good job here, region, you have a cross-section that could be substantially bigger. This is this gravitational gravitational focusing factor here, and it's a function of the escape velocity of the object, which scales as the mass of the object, and the relative velocity of the other smaller planetesimals. And if you assume that this is a constant, you can go through, and what you find out is the mass accretion rate goes as the mass to the 4/3 power. And as a result, if you have two guys that are almost the same mass, this guy will grow faster and run away, right? So you have a situation, if you start off with objects that are roughly the same size, this is a calculation where we started off, I think, with 7 kilometer objects, just let them go, you see that a few guys become dominant, okay, at the expense of all the other guys. But remember I said that to get this 4/3 power, you need to keep that constant. So runaway growth only goes to a certain size. When the big objects actually become large enough to stir their own soup, that they start gravitationally scattering their smaller neighbors, what happens during that, what we call viscous stirring, is that the ratio of the escape velocity, I can't reach, right? A pointer. The ratio of the escape velocity to the relative velocity wants to be roughly constant. And as a result, m dot now goes as m to a power less than 1. And so now, if you have two guys that are roughly the same size, the smaller guy can catch up to the bigger guy. And you end up with a situation where you have these planetary embryos that are all roughly the same size, feeding mainly off the planetesimals that are around, and slowly competing with one another as they grow. We call this oligarchic growth. Let me show you, now this is the same simulation I just showed, but now we're going longer. And you can see that we end up with a population of nearly like-sized guys embedded in a sea of planetesimals. Now at this point, right, things are still pretty quiescent. Right? The big guys here, they're jostling one another, but they're mainly eating off of the planetesimals. Right? They're on nice, relatively circular orbits. Every once in a while, two of them will run into one another, neighbors, and grow by accreting one another. Right? But it's still fairly quiescent because of two effects. First of all, there's dynamical friction with the little guys. Right? If you have a population of big guys and little guys in a disk and they're gravitationally interacting, you sort of want to get to an equal partition of energy, where the big guys have small eccentricities and inclinations and the little guys have large eccentricities and inclinations. Right? That keeps the big guys well behaved. And also at this point there's still gas around. So there's the dynamical interaction between the growing embryos and the gas that keep them on nice, fairly well circular orbits. And so you have a competition where the number of big guys is decreasing, the masses are increasing, right? The separation increases, but they're fairly well controlled. And this, in the inner solar system, goes until about the size of Moon or Mars, or 1 AU. But it can be quite large in the outer solar system, according to the standard picture, up to 10 Earth masses. And that'll become important when we talk about how giant planets form. All right, in the inner solar system, right, this goes on, but like I said, it only goes on until the time of which things are about Mars mass, okay? And it keeps going until the damping, whether it's gas or planetesimals, is too weak to keep the big guys cool. Now, let me take a step back. I have an apology. I know you guys are all chemists, right? A lot of you are. I'm a dynamicist. To me, cool and hot has nothing to do with temperature, okay? To me, when it's cool, it means the relative velocities are low. So the eccentricities and inclinations are small. And if it's hot, the eccentricities and inclinations are big. I have to apologize, but this is just the way I talk, okay? And I know I'm going to forget to do it right. So just remember, when I say cool, I mean low relative eccentricities and inclinations. And after the damping becomes too weak, all hell breaks loose in the inner solar system. So here's a plot that's going to be an animation of eccentricity versus semi-major axis. Okay, there are two populations here, planetesimals and embryos. This is by a calculation that Dave O'Brien did almost a decade ago. It's a little frightening to think about. These locations show the location of mean motion resonances with Jupiter, which in this calculation is on its current orbit. And so what happens is when the damping goes away, the embryos start scattering each other all over the place and start to grow. I should say I color-coded this so you can see how much mixing there is. And you end up with something that actually looks pretty good, right? You have an Earth, you have a Venus, you have a Mars, you have an asteroid belt, right? The asteroid belt is dynamically excited, and the mass is depleted, right? Because as we know, right, you look in the asteroid belt now, there's a roughly 99.9% of the mass that was there originally is now gone, right? So we have to get rid of it. And in this particular model, and this is an idea that was originally George Weatherall's actually, is what happens is you see you'll get planets growing here, but as they scatter each other around, they hit these mean motion resonances which drive up their eccentricity and allow them to be accreted by the Earth, right? So this is the argument, the current argument of where Earth's water came from, by the way, is that these water-rich objects out here get dynamically excited and then get accreted by the growing planets. I should also point out that the time scale for this is roughly 30 to 100 million years, and that's about what we see for the moon-forming impact from a cosmochemical point of view, so it's also consistent with the timescales in this problem. So that's pretty successful. Now for the giant planet picture, if objects grow something like 10 Earth masses before the gas disk goes away, they can directly accrete gas from the nebula, right? And so, remember I was talking about this transition from oligarchic growth to runaway growth. In the standard picture, the oligarchs get big enough to do this. And that leads us to the formation of Jupiter and Saturn. I'm sorry. I'm not going to talk about Uranus.
They've heard enough about it here, don't worry.
Yeah, I'm sure they have, actually. And the other new part of this picture I like to add in these talks is the idea that this process, or the process I'm going to talk about, of planet formation, right, there's nothing in that process that will naturally lead you to stable planetary systems at the end. There's nothing, the system as it's growing, there's no physics in there that's going to naturally produce stable systems. So quite often a system can become dynamically unstable. This leads to high eccentricity of few planets, which is consistent with some of the extrasolar planets systems that we see. And for those of you who've heard of this little thing called the Nice model, right? This is also a representation of these kind of instabilities in our own planetary system. Okay, so now I'm going to talk about problems. Anybody have any questions? You guys are way too quiet for me. You probably heard all this before, right? So,
No, not lately. A lot of folks are
all right.
it's new.
Okay, so there's three major problems that people have known about for a very long time with this standard picture. The first is what we call the meter barrier. And there are three aspects of the meter barrier that, well, there are three different physical mechanisms that make it problematic of growing things larger than roughly a meter size. First of all, I don't think anybody would argue, especially if you looked under my bed at home, right, that if you have really small objects, electrostatic forces can allow them to accrete, right? I've got these dust bunnies, you can blow on them, and you can watch them grow under my bed. It's a great experiment, okay? And of course, if you get big things, tens of meters in size, two things come together, gravity can hold them together, okay? But there's a distinct problem when you try to take an object this size and have it to accrete with this size, right? The electrostatic forces aren't strong enough, and the gravity isn't strong enough. So it's not clear that if two things like this hit one another, they will grow. But even if they could grow, it's not clear that they would, because the impact velocities between something this size and this size is going to be big. And so let me take a little aside and talk about that, because this is going to be very relevant to the Pebble accretion models that I'm going to talk about later. If, disks are pressure supported, which means that at any location around the sun, their velocity around the sun is going to be slower than the Kepler velocity. So if you have an object with, let's say, planet size sitting in the disk, it's going to feel a headwind due to the gas, okay? So the big guys, and I've got this probably in the wrong order the way I said this, a really big guy will feel this headwind, but it won't be very affected by it. A really little guy, and you keep this room pretty clear. I usually try to point to the little specks of dust floating in the air, but you just don't have any. So, oh well. You get really small guys, and their stopping times are so fast that they just sit in the disk, and they follow the disk around and do what the disk wants them to do, and really don't have their independent dynamics. Where in the middle, right, is where things become interesting from planetary formation point of view, where the object's stopping time is on the order of their orbital period. Then they're starting to decouple from the gas, okay? And they're trying to orbit the sun at the Kepler velocity. They feel this huge headwind, which is blowing them around. And as a result, what happens is that they start migrating inward because of this headwind. And if you just leave them alone, so here's an animation of radius versus semi-major axis and the minimum mass solar nebula, right? So we're about a half a meter here. What happens is these things migrate and spiral into the sun. timescale there. It's hugely fast, right? So these are about, you know, something on the order, we call them pebbles, right? So they're on the order of this size. Okay? So for those of you who are French, right, it's funny. I talked to some French people now, we don't get this, we don't get this. It turns out they have this character in France, but her name is in Pebbles. So they were very confused. So for those of you who don't know, this is Pebbles, meet Pebbles. Mr. Pebbles. Yeah, just lay them down here. Sometimes I keep her in my hand and people complain it looks like I'm strangling her through my whole talk, so I better treat her nicely. So again, if you look at this again, when it comes to this discussion of the meter barrier, what happens is these guys are moving at a very different velocity than those guys. And so rather, when they hit at very high velocities, and that would break them rather than allowing them to grow. Okay, and the third thing that has to do with the meter barrier is this exact issue of the flow inward. And that is, you have to have these objects grow fast enough before they spiral into the sun. So there are three issues that stop things from growing much bigger than this. And if you put it all in a big code, which I like to do, right? So this is, again, particle radius versus semi-major axis, and the lighter the color, the more particles there are in this calculation. You get up to about a meter and then just stop. Things can't grow. So that's the first problem the standard picture has. The second problem is what we call the giant planet core timescale problem. This is what Alan was trying to solve when he worked on his model of giant planet core formation, or giant planet formation without a core, right? It's one of the ironies that my field is faced with, that the largest planets in the solar system had to form first, because they're made mainly of hydrogen and helium, so they had to form, and the gas disk was still around. And if we look at data from star clusters, this is the fraction of stars that have disks. By the way, these are infrared excesses, right? So they're not measuring the gas. We can't measure the gas in other planetary systems. As a function of age, if you believe this is a proxy for gas disks being around, you can see that 50% of the disks go away in 2 or 3 million years. Okay? So we have to build Jupiter and Saturn on that time scale. And the way historically people have tried to do this is, remember this equation where the mass accretion rate goes as the cross section, which has this gravitational focusing factor in here. And the way people have tried to do this is by keeping the relative velocities very low. That makes this factor very big and the accretion times very fast, okay? But remember, the embryos, because of the gravitational interactions with the planetesimals, want to keep these numbers comparable to one another. And so what people have traditionally tried to do is keep the relative velocity really small, okay? So we looked at this, again, my role in this field is to do these large n-body calculations. A couple of years ago, Martin Duncan, Ed Thomas, and I looked at this, and what we found is if you keep the damping high enough, rather than getting accretion very high, what happens is that these guys will scatter the planetesimals. Notice they're scattering them out, and then drag is, this is using aerodynamic drag, physical collisions will also do this, drag is circularizing their orbits and keeping them cool, but it's doing it away from where the planets are. So instead of having a large accretion rate, what we find is that you open up a gap, right? Think Saturn's rings, and things won't grow. And we played with lots of different particle sizes, gas distributions, and the whole thing, and we never found a sweet spot where you could get a lot of growth. Either the system was too dynamically excited, hot, or you opened up a gap, but never in between. So trying to keep the embryos cold hasn't been able to work. Now, Pebbles solved this problem, and I'll talk about that in a minute. But at least for these macroscopic planetesimals, things didn't work.
Before you leave that, how big are the green objects?
These, they started off as an Earth mass.
It's just curious, if you can, it seems like you can create some fairly large cores at about sort of 3 to 6 AU in that model.
Well, the largest thing we got was 2 Earth masses.
Oh.
Okay, and that happened almost immediately when we had a uniform surface density of planetesimals through here, so these initial conditions would never happen, right? Because when these things were smaller, they'd be scattering things around. Okay, the third idea this was a problem first pointed out by John, I think in 2001, is that right? So it's been around a long time. Is that right, John?
I believe so.
Yeah. Okay. And that is, remember I showed you this model before, and I argued it looked pretty good at the end. It's good in the end, right, with an Earth and Venus and a nice asteroid belt. But look at Mars. Mars is the same size as the Earth, which is not true, right? Okay. And indeed, this is a systematic result of all these simulations of this, is that Mars is an order of magnitude roughly smaller than these models. Matter of fact, notice, right? I said Mars is too small, right? I didn't say that our models predict planets that are too big. I'm a good theorist. The problem is with observations, not with the theory. No, okay. So here's a plot of, again, this is taking many simulations. This is by Sean Raymond a few years ago. Many simulations. This is mass as a function of semi-major axis in his simulations. And you notice, forget about Mercury. We'll talk about it later if I get a chance. You get you get Venus, and you get Earth and Mars, and the models do a really good job of getting Venus and Earth, but fail miserably when they get to Mars. And indeed, a recent paper by Fred Chesla, and I think a graduate student, where they did a bunch of these things, say the standard model gives a reasonable Mars only roughly 4% of the time. And indeed, as I pointed out before, this is probably the oldest plot in my talk. This is a surface density profile that Stu Weidenschilling came up with a very long time ago, where he took all the planets, ground them down, made them into an annulus, and then reconstituted it up to solar composition. And he pointed out that we have this nice parallel relationship for the surface density as a function of semi-major axis, except for Mars and the asteroid belt. And the asteroid belt's almost 4 orders of magnitude depleted.
Hal, I think Stu published that when he was here at ETM, actually. So
is that right?
Yeah, it's nice linking around.
Okay.
Yeah.
Yeah, I didn't know that. How long was he here?
He did it for a couple of years as sort of a postdoc.
Oh, cool. I didn't know that. Okay, so if you then go back and again in Fred and Fisher and Chesla's simulations, and ask what fraction of the time do you get a reasonable Mars and a low mass asteroid belt, it's less than 1% of the time in the standard picture. So there's a problem. The other thing I should point out is that the standard picture does deplete the asteroid belt, but it's very clumpy, right? You get regions where things are excited and regions where they don't, and gaps where the embryos were, and if you actually look at the asteroid belt, it's remarkably smooth. So that's a problem there. Okay, so let's move on to Pebble accretion. And I think Pebble accretion potentially solves all these problems. Okay? Now, I have to say, I'm going to use a very broad brush when I talk about Pebble accretion. It's combining several different ideas, sometimes competing ideas, and quite often by people who really don't like each other, right, in a very broad brush, okay? So, and I'm sure if some of them were here, they would really be upset that I'm calling these things Pebble accretion, or what they're calling Pebble accretion. So dust, the basic story is the dust particles begin to settle on the gas disk and grow by two-body accretion, like I said before, because of electrostatic forces. When they get roughly pebble size, right, they begin to become decoupled from the gas. And there are two independent models that have been put forward for what happens next. The first is called the streaming instability. Okay, and here's a animation of that model by Anders Johansson and his collaborators. This is just physical position here in X and Y. The sun is over here far away in this calculation. There's a turbulent gas disk here, but you don't see the gas, you just see the pebbles. And the color indicates local density of pebbles, okay? And watch what's happens. What's happening is you get these concentrations in the disk, which grow as a function of time because of this streaming instability. And here's a clump. That's roughly the size of Pluto, okay? Or the mass of Pluto. It's bigger than Pluto. And essentially what's happening here is this. Remember I said, if you have a pebble in a gas disk, it's trying to radially migrate. If you actually get a clump starting to grow in the pebbles, they start acting as if they're a larger part. They can start pushing the gas around a little bit, so they start acting as a slightly larger object, in which case their radial velocity slows down. As a result, this guy's moving in more slowly than a pebble, and the pebble comes by and hits it, it can get trapped, right? And that's a formal instability where things can grow. The other idea was put forward by Jeff Cuzzy and his collaborators, where you actually have turbulence in the disk, and centrifugal forces in the turbulence eddies force objects to migrate outward, and they start concentrating at the corners of the turbulent eddies. In either case, you get the particle densities high enough, the pebble densities high enough, that these objects become gravitationally bound and collapse to form macroscopic objects. The cool thing about this is that these objects tend to be 100 to 1,000 kilometers in size. So you have a disk, the disk is full of things like that, they get together and collapse to form things the size of Pluto. This is very, very fast, okay, on the order of a couple orbital periods that this happens. So this circumvents the meter barrier, because you really never have objects that size. You go directly from things like, remember, I'm not hurting, okay, things the size of this to things the size of the big asteroids that we see in Pluto overnight.
Al, why don't you bounce at that size though?
Excuse me?
Why don't you bounce at this size?
Because their velocities are small to one another. The gas gets them so tight that they become gravitationally bound. They're like star clusters, and then they slowly settle. So one interesting aspect of this, from people interested in cosmochemistry, is that when these things come together, they come together at their terminal gas velocity, not as if they're coming in from V infinity. So their accretional energy is actually swept away by the gas, and they touch at very low velocities. So the accretional energy you normally think about is not there anymore. Be interesting whether that could be tested in some way.
So they start out as rubble piles rather than consolidated bodies.
That's right. And then heat up if there was aluminum around. Yeah.
But at this stage, and is the temperature rise and rapidly, or are we still talking about very cool stuff?
It's very cool stuff, because let me just say, I don't know if anybody's actually looked into this problem. My intuition is they're very cool stuff, because what's happening as these things come together is they're heating the gas, but the clumps are moving with respect to the gas. So that energy is being swept away, being mixed into the nebula, and I believe these guys would stay cool.
At least in the original models, the pebbles were very high density, i.e. 2 to 3 grams per cc, and it's never been clear to me how you make those. I don't know if things have changed, and you know, to make
You mean the bulk density of the pebbles themselves,
My memory is correct, yes, that was the assumption.
I don't think it matters. All that matters is what is the Stokes number, this ratio of orbital period to stopping time, I think. So I think that would just affect which objects this would be effective for. But I don't think it's going to affect the ability to happen. The real weakness with this is that you need a high solid to gas density, right, in the disk itself, right? So what these guys are arguing is you get rings forming, right, and then those rings become unstable, right, because you need a local metallicity of roughly 3 times solar to get this to happen. And this is, of course, just the streaming instability. There's also Jeff's stuff, which I'm not going to talk about because I don't understand it very well. Yes?
If the temperature at the center is not high enough, then its pebble situation is not going to change very much. Consequently, could you send a thumper to detect a quake?
That's a good question. I haven't thought about it. You have to be careful because there is aluminum-26, which will heat big bodies. So if these things form over the first million years, and the people in the audience clearly know more about this than I do, right, the objects are going to melt anyway. Yes?
Since you're starting out with pebbles and ending up with rubble piles, I think you need to work Barney Rubble into your stories.
I'm not done. But I'll have to do that. Okay? That will make 3 instead of 2. But I have another spin on this. So anyway, this is not very efficient. So you end up with a bimodal distribution, right, of objects. You have these 100 to 1,000 kilometer planetesimals, if you want to call them, embedded in the sea of pebbles. So I think the real advance that's come in the last few years is by this Anders Johansson guy and his collaborators who showed that if you have an object that's something like Ceres size or Pluto size, it can grow incredibly efficiently by directly eating these pebbles. And the story is this, right? In the standard picture with no gas, if this is a planet, it's orbiting the sun is that direction pretty far away, right? Typically, if you come far away, you'll just get a gravitationally scattering event. And this guy can only grow by eating things that come in this fairly narrow angles. But look what happens if we start working with pebble-sized things. Same object, it feels a little aerodynamic drag, which slows it down. It becomes gravitationally bound and spirals in and gets accreted. This allows these objects to accrete from a huge area. Here's a plot, for example, this is the accretion cross-section as a function of the mass of the object, or its radius. I think I'm assuming a density of 3 here, but you get the idea. Here's the physical cross-section. Here's sort of a standard viscous stirring radius of cross-section. Here's the Hill sphere, which is the gravitational sphere of influence of the body. It's huge. For the Earth, it's something like 1/100th of an AU, I think. You really should know that. John, do you know that?
Yeah, that's right.
Okay. Okay. And here's what you get from pebble accretion, and if you get above something the size of Vesta or so, the cross-section becomes large enough, even larger than the Hill sphere. This is huge, right? This is R, right? The cross-section goes as R squared, so this is, what, 6 orders of magnitude. Boom. These things are huge. So if you take a object, let's say 500 kilometers or 1,000 kilometers, and just put it in a sea of pebbles, this is the accretion rate as a function of time at 5 AU. Okay? It goes from teeny things to 10 Earth masses in 1,000 years, right? This is incredibly fast, okay? So if you were 1,000 kilometer size object, I'm gonna go back to this. you would be suffering 10 to the 7th collisions a second of objects this big, right? Every square meter would be hit every 12 days, or an area the size of Boulder would have 100 collisions a second. Okay, so if you were standing on this thing, which I wouldn't recommend, right, it would look like it was snowing pebbles. Right? I should do a little animation. It's huge. The other thing I want you to notice about this is there's this cutoff. Big objects will grow, little objects won't. And this cutoff is due in part due to the fact that in order to have pebble accretion to work, if here's the planet growing and the pebbles coming by, the stopping time due to aerodynamic drag of the pebbles has to be comparable to the encounter time, right? If it comes by too fast, then the pebble won't get slowed down, and so it won't be affected by the gas. And so for smaller guys, the encounter time's faster, and therefore it won't work for the small guys.
So does that set a limit on the pressure that must be present in the gas during the disk?
It sets, well, there's going to be a relationship between the size of the pebbles, right, and where things can grow and where things can't. So this is using sort of standard numbers at 580, right? So you know, 500 kilometer size guy will grow while a 200 kilometer size guy won't. This becomes important in the story I'm going to tell in a few minutes. You ready? Okay. So we're done, right? We can, you know, we had this problem with the timescale problem with the giant cores. I just showed you I can build a core in 1,000 years. Right? That's plenty of time, we're done. Right? So why is this guy frowning? Right? And the problem is it doesn't work in detail when we put it into full n-body calculations. So we're using this new code which called LiPad, which does both dynamics and collisional evolution of the disk. Particles, we use relatively reasonable numbers for the surface density disk and all this. I won't go into this. And indeed, if we set it all up the way Lembrecht and his collaborators expected, this is what we see. So this is now size versus semi-major axis. Here are the pebbles, here are the planetesimals. And watch what happens. These things drain through the disk pretty quick. Look at these things grow, man. 1,000 years, right? We have fairly big objects, 10,000 kilometers. Remarkably fast. But the problem is, let's look at this in another way. Instead of just showing you the individual objects, I'm going to show you a size distribution. So this is mass and number, and this is cumulative number. Okay? And we start the thing going. And the problem is it works too well, right? At the end of the simulation, the largest object is still only a couple Earth masses, but we have something like 400 objects bigger than the Earth mass. Right? We have 4 giant planets. This isn't going to work so well, right? And the problem is these things grow so bloody fast, right, that they're sitting there and they're growing faster than they can dynamically interact with one another.
What was the nebular mass?
This was 3 times nebula mass or something like that. I don't remember. Okay, but I mean it doesn't matter. We tried all sorts of things, and I'll explain to you why this is sort of generic problem with this particular model, right? So these things grow so fast that they can't see each other dynamically, and all of a sudden at the end they go, wait, there's an Earth mass thing sitting there, right? And the system just goes, bam, right? And they scatter the hell out of one another. You might have a couple bigger guys grow, and you occasionally get a core, but these Earth mass things are flying all over the solar system. They destroy the Kuiper Belt, they destroy the terrestrial planet region, they destroy the Asteroid Belt, they destroy everything. This isn't right. So what's going on? Oops. What's going on has to do with the shape of this curve. Right, early on, this curve is steep. As a result, the mass accretion rate goes as the mass squared, which is very fast, and it's a runaway, and only a few guys grow. But once you get over something like the mass of Venus, this flattens out, right? And what you get is a situation where the mass accretion rate goes as the mass of the 2/3 power. Oh my God, I'm sorry, I haven't even gotten my stuff yet. Okay? And so as a result, they all grow like oligarchic growth, and they all grow in lockstep with one another. So that's not right. I'm going to speed up. So let me just say, I was very happy. First of all, when you look at their equations, I knew this is what was going to happen, and I was very happy because when I read that paper, I hated it. Okay, I really did. I had my own ideas. I just wanted this idea to go away. Okay, I saw this flaw. I did these calculations. I said, "Oh, thank God it's dead. I can move on. Right? Let's write the paper and move on." But I thought to myself, well, we're making the assumption that all the pebbles are there at the beginning, right? But if you look at disks, you see that they have infrared emission up for millions of years, right? So there must be some dust there over long periods of time. This would predict that this becomes optically thin very quickly. So what happens if we just allow the planetesimals to grow, or the pebbles to grow over a long period of time, okay? And I thought, well, maybe what would happen is these growing planets would accrete one another, and therefore we'd end up with a few planets. And I better run that one test. That's not what happened, but we discovered something significantly better. So let's now just let these things form slowly over time, and look what we get. We get 2 giant planets, a couple of ice giants, and nothing down here, okay? And indeed, that's the planetary system that I end up with in my favorite calculation, right? You have Jupiter, a Saturn, Uranus and Neptune, and a couple other things floating around, and the Kuiper belt that survives, which is what we need in these calculations as well. So this works pretty well. And what's happening is, as these things start to grow, so I should say the pebbles are aerodynamically cold, so their inclinations are small. But as the planets start to grow, they start dynamically exciting one another. And since they want to get to an equal partition of energy, right, essentially what happens is the little guys get scattered away further from the disk. Purple's where the pebbles are, right? These are the embryos, and the error bars are essentially the cross-section for accretion. The little guys get scattered up above the disk, and they're starved. They can't grow. While the big guys like to hang around in the disk, and they can grow. And as a result, only a few guys can grow, and you'll end up with a small number of terrestrial planets. I'm sorry, I'm running late. So I'll try to speed up as much as I can. So this is what we call viscally stirred pebble accretion, and it reproduces the giant planets that we see. So the next question is, can we apply that to the terrestrial planet region and explain the low mass Mars? And the answer is yeah. Remember I said that there was this cutoff, right, in growth, right? As we talked about, somebody asked, right, this is a function of the local gas density, right? The size of the pebbles and the local gas density in the disk, where big guys will grow and little guys won't. So you can model that as the Hill sphere to some power, to some exponent, where this exponent is a function of things like the size of the pebbles, the size of the growing planet, the gas density, and the orbital period, essentially. And you can plot this value as a function of the size of the planet and the heliocentric distance in a reasonable disk, right? Over here you can grow, over here you can't because it's large, and this is series. So if you just take series and put it in a reasonable disk, it can grow at 1 AU, but it can't grow at 2 AU. Okay? So let's ask what happens when we put something like this in a disk. So we're going to start off with a population of planetesimals that are a significantly small number of objects. Only, in this case, something like 1.5 Mars masses. Spread all the way from a half an AU out to 2.7 AU, where we assume the snow line is. Here's the surface density of material in that disk, okay, at time equals 0, and we just set them the sizes that are consistent with the currently observed asteroid belt. That's it, okay, up to the size of Ceres, okay, and we put this in a big body calculation, and we find that the terrestrial planets form in 2 stages. While the pebbles are here, you can see them streaming in here. Top shows the surface density of the disk. This is what the surface density scale looked like at the beginning and what you would expect in a standard picture. And notice you get this sharp cutoff and where things grow. Stuff down at 1 AU grows quite effectively while nothing much happens in the asteroid belt. Okay? And you end up with this population of planets, the roughly 20 small planets. Look how that are systematically smaller as you go out to the inner part of the solar system. Now this system is remarkably stable, right? And you can just, they'll hang around for a long period of time. Here's now eccentricity versus semi-major axis with these planets and the asteroid belt, starting at 2 million years in the calculation, and they are being damped by the presence of gas, mainly, but as the gas goes away, they go unstable. And this is where all the giant impacts happen, okay? It's during this phase, right? So the first phase we call the Pebble phase, right? And because of the giant impacts, the second phase we're calling the Bam Bam phase. Oh. And look, we basically reproduce the solar system that we see, Earth and Venus and Mars. And indeed, if you want to look at it in more detail, now I have to say, these calculations are extremely time-consuming. They take months, okay? And there are lots of free parameters. So we haven't been able to look at the full range of parameters, but this is a plot of essentially massive planet as a function of the semi-major axis. Here are the four terrestrial planets, and this is the distribution that we see. More importantly, here's cumulative fraction as a function of our mass analogs, which are essentially looking out through here. And you can see that we reproduce something smaller than Mars about 30% of the time. So I think we do a pretty good job. We also do a decent job at reproducing the asteroid belt. Okay, here's again a cumulative fraction from our simulations. Again, remember we're not uniformly covering parameter space. It's also not clear how to define asteroid belt in these simulations. The min-mass solar nebula would have you somewhere out of 3 to 5,000 in this measure, which is the mass of the asteroid belt. And you can see we get a few, we get low mass asteroid belts out of our simulations. And here's the excitation of the asteroid belt, which we reproduce pretty well too. So we get a good asteroid belt. I mean, this was our target. This was built into our calculations because remember I said there was no growth in the asteroid belt. So this is essentially our initial conditions. And we tried to make it bigger because the Nice model and grinding and things like that will get rid of something like, half to, to 30%, 60% of the asteroid belt over its lifetime. So that's what's on. Yes?
Sorry, so I missed, what is the fundamental difference between why things are growing to 10 Earth masses quickly at 5 AU and to 1 Earth mass at 1 AU?
You're leading into my, I'll actually stop here. So there's 2 fundamental differences here, okay? In the calculations for the terrestrial planets, we use Ceres as our largest mass. And in the outer planets, we're using Pluto. So we're using the Kuiper belt in the outer planets and the terrestrial planets. So 1,000 kilometers can grow out here, but 600 can't there, right? It's an assumption. It's reasonable. The other thing that I didn't mention, and Larry, you're supposed to remind me, is that we're assuming pebbles forming in the outer solar system cannot get into the inner solar system. This is a cosmochemical argument because those things would be all carbon rich, and the planets don't have, Earth and Venus don't have a lot of carbon in them. So we're assuming that they're icy and they hit the snow line and just go poof, okay? And what happens to that mass, I'm not sure, right? But I think that that's pretty reasonable assumption. The other thing that in these particular models, and I don't know if this is necessary, but this is just the region of parameter space that we found works, is the pebbles are actually bigger in the outer solar system than they are in the inner solar system, okay? But they're all have Stokes numbers less than 1. And since ice is stickier, the idea that they're bigger in the outer solar system seems reasonable to me. So let me just put it all together. But this is the same disk, and it's using the same physics.
And the gas is going away at some point?
Yeah, it's a 2 million year exponential decay. Earth, Venus, dynamically excited asteroid belt, Jupiter, Saturn, ice giants, Kuiper belt. From the
It's
same
just too
process.
computationally expensive to put it all in one. So
It is, I mean, this is a killer, okay? Even what we're doing. Now, I'm going to stop. I could talk about Mercury, but I won't. But I have to say that I cheated on these giant planet calculations a little bit, because when it started to accrete gas, I think we've got most of the physics reasonable up to where does a gas giant stop growing, right? Because that's hard to do. It's gap opening and stuff like that we don't have in the model. So in this particular calculation, although not in the paper we recently published, but in this particular calculation, the largest guy we let to grow the Jupiter mass, the second largest guy we let to grow the Saturn mass, and then we stopped anything else from growing, okay, very much, to get the ice giants. All right. Now, typically, if we don't do that, we end up with between 0 and something like 4 Jupiter mass things, and no Saturn or no ice giants, because we don't. Well, we occasionally have ice giants, but we don't know when to stop the growth. And this particular calculation actually was designed not to do the giant planets, but to look at the effects of the giant planet formation on the asteroid belt dynamically. So we actually stopped them at the right mass. But the order is something we didn't constrain, right? So we could easily have had the Jupiter mass thing further away. But I just wanted, in all honesty, to inform you of that. Okay, so that's the basic story. I'll stop there. Okay. I think this idea can also be applied to why there are no planets in the solar system inside the orbit of Mercury, but I'll have to go, if you want to ask me about that in private, we can certainly do this. But I think I've said all of this before. I'm soft money, so I want to thank my funding people. And if you want to see more of this done, send money. That's the message. Any of my talks. Okay, thank you.
Whoa, questions, right. Let's start, Bob, I think you had your hand up first.
So I've got 2 questions. One specifically, as a mineralogist, I'm trying to visualize these pebbles. I
what?
can see electrostatic dust bodies. I can see
Minerals.
perhaps condensation of ices and so forth, but something that's sort of this size and solid, I just don't see how that happens. And the other aspect of this is, you've done a very nice job of reproducing a kind of quasi-R solar system, but as we know from Kepler, there are many, many other very, very different kinds of systems. So why are they different?
So to answer your first question, the only parameter that matters for whether this works or not is this Stokes number, the ratio of the orbital period to the stopping time. I'm making no assumption about the internal structure. Dust bunnies would work as long as they have the right Stokes number. Okay, and I think that answers your question, right?
You need a lot more of them.
They need to be a lot bigger, a lot smaller. Yeah, I guess they'd be lower mass, but that's right. But remember, the constraint that we have is the total mass of solids in the disk. Okay, and that is our constraint. And whether there are a lot of little guys or a small number of bigger guys is irrelevant. You have to use all that mass. Okay. To answer your second question, that's one thing I like about this model, And to take a step back, there's sort of been, at least in my mind, a philosophical shift in the planet formation community since Kepler and the extrasolar planets were started. When I started this game, people would say, look, we have our solar system. Any model you have has to reproduce our solar system, right? And they want it to be generic. They don't want, they were very uncomfortable with this idea of fine-tuning the models in order to get the region that reproduces what we see. And I think that that's changed. Okay, there are a lot of knobs in these models. Of course, I'm showing you the region of parameter space that I stumbled on that actually produces what we see. But there's a huge parameter space, and the hope is, as we start dialing our knobs, we'll be able to reproduce the other ones as well. I mean, that, this characteristic of these models is both a curse and a blessing, right? It makes a lot of people uncomfortable, but I think that's the way, the observations show that's the way the universe actually behaves.
John, I think you're next.
Uh-oh.
Migration.
Hell with it. No, in these particular calculations, migration is turned off. Okay? The beauty, again, of Pebble accretion is the free parameter we have is the rate at which you create pebbles. And, there's really very little constraints on that. So, to get all this to work in the giant planet region, like I said, you need to create the pebbles on a time scale that's long compared to the viscous stirring time. But that's fairly short. All right? And so, perhaps you can get things to go through the type 1 migration time fast enough that it will save them. In the terrestrial planet region, I think it's more problematic. The thing that I'm doing to try to explain the lack of Mercury objects actually is trying to invoke type 1 migration with this, right? Because if you remember, I showed you this plot showing the mass of a planet as a function of heliocentric distance, right? The type 1 migration time, right, and it was pretty steep. Matter of fact, it was an exponent because it was a log linear plot, okay? And so the argument is planets grew really big at 4 and 3, and those migrated into the sun, while the stuff that further away did not. That's the idea we're playing with, okay? I haven't gotten it to work. I've been spending a hell of a lot of time on it, but we can talk about that later. I can show you some results of that.
I think Con was next.
Yeah, I guess the last two questions have touched on some of the things I was going to ask about. But certainly, Anders Johansson is now talking about in his Pebble accretion models that he has to make the cores out of 20 AU and that they migrate in. It's got Alessandro popping mad, but that's what his models are saying, and that was presumably quite problematic, if I understand it correctly. My other question is.
So let me respond to that, okay? If you look carefully at these calculations, what we find is the giant planets start to grow at the transition between Stoke and Epstein drag, not at snow. And that's because the characteristic radial migration changes, okay? And pebbles spend more time hanging out there. Interesting result. Okay, who would have thought that, right? Then so that depends on pebble size, right? So that's what we're finding, okay? And then the whole disk fills up. But I could easily imagine forming them pretty much anywhere, depending on your assumed distribution of planetesimal sizes. So it's the step beforehand that I think is more critical. So I didn't know that Johansson was arguing they formed further away. That didn't happen in the calculations I just showed you.
The other question or point is that Mars features very heavily in rejecting the classical model, but it seems to me that a 1% chance, given the diversity of planetary systems that we're finding from Kepler, that's not a very strong constraint anymore.
Well, it was 0.5%.
Or 0.5%.
Okay. I tend to think it is, unless that's 2 sigma, or 3 sigma. you know, if it were a few percent, it wouldn't bother me. But an order of magnitude smaller than that, I mean, I think it's really a question of whether we can be in the solar system that has a big Mars and an asteroid belt.
What
Right.
what
So-
is the fraction of solar system like planetary systems in the Kepler and radial velocity?
We don't, it can't get, we're not down to the point where we can see our solar system yet. The Kepler data set is mainly planets that are much closer
Well, it's
and
not
larger.
just Kepler, but we have the radial velocity measurements too.
Yeah, but they can't see Earth's either.
But they can see a Jupiter.
Yeah, my understanding is Jupiters are actually fairly rare. Okay, so that's not a constraint.
It's roughly 10 or 20% inside 10 AU. So it's a small fraction, but not zero.
And we're just getting to the point where we can see Earth and Jupiter and Saturn. Because of the moon the time scales.
Yeah. Yes, please.
Let me see if I can pose this question right. We know a lot more about extrasolar planets now. Your concentration has mainly been on the solar system.
Yeah, we have more data for the solar system.
Yeah, but you also have data that are statistical with regard to the extrasolar planets.
Yes.
You can do averages, you can do distributions, and so on.
Yeah.
And if you look at that in terms of broadening your parameters that you're using for the solar system, I'm wondering whether that gives you any insight into the formation of the extrasolar systems.
Undoubtedly so, okay? I mean, the problem that we're faced with, I think, okay, it's always been my bias to concentrate in the solar system because of the, you know, the large amount of data that we have, right? And the ability to do statistics, like you said, is only recent, right? Only within the last couple of years. The problem that I see of trying to apply this without proving to ourselves it works here to extrasolar systems is that we have all these free parameters in our models. And so there's a whole group of people that do what they call population synthesis models, right? Where they put in sort of heuristic ideas of how planets form, and they go and compare the distribution of their planets to the distributions we see in the Kepler system. And every time they do that, I raise my hand and say, how often do you reproduce our solar system? And the answer is, and that's the end of the conversation.
They can't even reproduce the Kepler data.
Well, that's true too. So, given the freedom and the free parameters, I'm very nervous about just assuming you know how they're varied in order to compare what we're seeing to that. And the model, those particular models, you know, they can tweak. They're missing a lot of physics. Matter of fact, a lot of what I said today they're missing, right? They're, you know, dial their knobs and they can fit the data or they can't, right? And that doesn't mean they're really understanding what's going on, right?
Yeah.
So I'm a little dubious with that.
I was going to say the most spectacular misprediction of the population synthesis models was that there should be a planetary desert for super Earths on short period orbits. Should not be very many 5 to 10 Earth mass objects with sort of a Mercury's orbit inside. Instead, Kepler has found it's a planetary oasis, and they're still working on trying to fix that one. That is the most obvious thing that they completely blew. So
That's right.
They're spinning their knobs like mad. Scott, did you have a question too?
Yeah, it was answered way back.
Okay. Erica?
So you're modeling the solar system, you're not worrying about population synthesis right now. It sounds like. So when do you consider the problem to be solved? I can run this.
Okay. Let me answer this in a very serious way, right? Like I said, I'm solving money. It's my problem. It's my job to find problems, not solutions. Okay, so hopefully never.
Well, when you retire anyway.
Yes, that's right. No,
It's about I'm asking about the fine tuning problem. If you can make a really nice solar system looking system.
I think it's our job, and this is sort of what we've done with the Nice model, right, is to push it until it breaks, right? And, you know, there's tons of issues, for example, that I didn't raise. For example, you know, to zeroth order, you might expect the cosmochemical composition of all planets, because they come from pebbles coming in from all distances, to be the same. Right? So how do we explain the differences between Mars, Mercury, and Earth, right? I mean, you know, do we really reproduce a reasonable asteroid belt at the end, right? I mean, there's a lot that we can do to probe whether this is right, right? I mean, we'll learn a lot by breaking it, right? So that's, I think, our next job.
Oh, okay. Scott, and then you, please.
Okay, well, just, yeah, I mean, one of my main questions was any predictions here. And so, if I understand right, you're saying Mars is too small because things grow faster closer to the sun and they grow less fast further out.
No, things further away can't grow, period.
So I guess as a prediction of other solar systems would be that you'd have smaller things further out in the terrestrial planet region. There would be some kind of gradient.
Not necessarily, because it depends. I'm sorry, there are novels. Okay, the idea that I showed you, for example, will only work if the disk is flaring, right? Which we believe they are, but not everywhere. Okay, it depends. Let me go back and show this again. Actually, okay, so this is, I showed you this plot, this is the size, this is distance from the sun, that series, this can grow, this can't, right? Okay, but this geometry only occurs, right, for a particular value of the Stokes number, right? So if all planetesimals were 100 kilometers, everything would grow everywhere, okay? So there's a relationship between the Stokes number and the size of the largest planetesimal, where you would get this cutoff, and not all solar systems would have it. Here, for example, is the same plot, only for something that's chondral size, right? And you see the same relationship, but again, you would need the things to be like 60 kilometers to get this edge to occur, and not all solar systems will have the edge.
Would you ever have it go the other way, though? So right now, you have a small Mars and a big Earth. You have a small Earth and a big Mars.
Yeah, because there's a process that Johansson actually talked about, which we don't see, right? Because I think we're doing the full dynamics, right? Is there's shadowing, right? That if the accretion of pebbles is efficient, they won't get through. So you can starve the inner regions from that. Okay. Now we never see that happen, but it could very well happen.
Okay.
Yeah, I'm sorry. I can. Right. This is a great theory. Give me a planetary system, I can probably grow it.
Last question, please.
Do the presence of Trojans give you any insight into your models?
Well, if you're a fan of things like the Nice model, which I am, right? The Trojans are not a primordial population. Okay, they get trapped during the migration of the giant planets. So let me just preface this. I'm a PI on a discovery mission to go visit Trojans. So I think they're the most interesting objects in the solar system. Okay, but I really do think they really do, they're sort of a dumping ground for the outer solar system. And there's a huge diversity of physical characteristics there, colors, things like that, that I think represent planetesimals from different regions of the protoplanetary disk. And so, yes, I think that by studying you could constrain exactly how things grew in the outer solar system.
Okay, so Hal will be here for the rest of the day, and I think part of tomorrow morning as well, perhaps.
I can.
So if you have some more questions for him, please ask them, and let's thank Hal again.
Thank you. No, I'm glad. It was really fun.
I'm sorry we took so long.
That's okay. I've always been curious. But
What is the thermodynamic temperature of the accretion equation?
So Larry,
Oh yeah.
This is something that is all the fault. People are like, oh, it evaporates, it's gone. Where? Where did it go?
Yeah. Well, I mean, I don't think in the region where we see planets it ever gets hot enough.
I don't.
No, because the disk was optically thick then, and the midpoint was cold. The main heating in the disk, this is not good, right? But the main heating in the midplane of the protoplanetary disk is actually due to viscosity and turbulence, not due to the sun.
Then you can use the computing meteorites as evidence of what it was really like. And if you look at the controls, they get like fused little shells in there that rise, and so that can give you some parameters to check against your hypothesis.
You're going to hate me. I don't think chondrules are relevant to this question at all.
Well, to me it seems that because they are created and melted, they provide some information about
I think it was a secondary process. Okay, and the argument for that is was given by talk, that if you put an object the size of a chondrule in a disk, it moves around a lot. And I think if chondrules were free-floating objects, right, that when you looked at a chondrite, you would see a diversity of objects within the same rock. Okay, and the fact is that you don't see that. Okay, and so it seems to me whatever forms chondrules have to be local and not part of this global process.
Right. Okay. Thank you. Thank you very much.
Thank you.
Hi.
Hi.
I'm Jerry Morton. Nice to meet you.
Nice to meet you.
Enjoyed your talk.
Thank you.
I've got a bunch of connections. The Naval Observatory, when were you there?
I was in Flagstaff from
DC.
DC, second half to 89 through 91.
Okay, I think I was already gone because we were in NOAA, right down the hill.
Okay.
Next to the Safeway.
Okay.
Anyway, Mark McCumber. Mark McCumber, did you know him? No. Okay.
Mark Morrison?
No, McCumber.
No, I don't know him.
Okay. Anyway, in Boulder, connections there. Stan Ruttenberg, do you know him?
Where is he?
In Boulder, but
Where does he work?
I can't remember. It was a long time ago.
Okay.
Been retired 15 years. So.
Yeah.
And then people at the Geophysical Data Center, do you know them?
No.
No kidding.
No.
Wow.
I mean, Boulder
Yeah, there's a lot of stuff.
Yeah.
Yeah.
We barely interact with the people at the university.
Oh,
We've reached a critical mass,
Well,
right?
where are you located?
In the city itself,
Yeah.
right downtown.
Oh, right downtown. Okay.
Yeah. How well do you know Boulder?
Pretty well.
So do you know where there's a brewery called Walnut Brewery, which is one of the on Walnut Street? We're right across the street from
I guess so. Yeah.
Okay.
Yeah. So
Yeah.
Because
Yeah,
I was
we're
asked for
still-
that
Yeah,
geophysical because that was part of I worked for
Actually,
NOAA.
maybe I can
I
do right now.
Yeah, I think it looks like he's
Yeah.
yeah, I mean, there's so much going on there, and the Earth people we really don't interact very much with.
Yeah.
It's funny.
Yeah, it was funny, at the Naval Observatory, a lady that worked for me, we have a party that's been going on for 30 years, once a year. And she has this friend now who worked at the Naval Observatory. The first time I met him, I said, well, what do you do at the Naval Observatory? He says, I find out which way is up. All the time I've ever talked to
Yes.
anybody. We also did that, because we did it forever.
Yeah.
That was the funniest thing.
Pebbles and Bam Bam.
Pebbles and Bam Bam. So,
Thank you.
nice meeting you.
And how do you party rubble?
Now I've got a rubble, so
No, but I guess Bam Bam's the name is rubble, right?
Very good. Yeah.
yeah, thank you.
I'm shutting down the system, so.
Oh, I'm sorry. Let me get out of your way.
You're okay.
Got your mouse?
I've got to get my mouse.
Yeah. Yeah, that's.
So we're having a pizza lunch next door in 10 minutes.
All right.
Actually, I can take this.
I said a throwing away party for a postdoc.
Oh,
Yeah. So
where are they going?
I don't. Oh, she's going to France
Switzerland
and Switzerland. Yeah, she's
French.
Okay.
but she accepted an offer in Lyon or somewhere, and then got a much nicer offer from ETH in Zurich. So she's, I think, doing the French one for a short time, and then moving to Switzerland.
Okay.
Something like that. Anyway, she's a isotope geochemist.
Oh, so it was good that I. introduced who the characters were.
Oh, absolutely.
Because
no, there's a wide range of people in this audience today. That was a very, very wide range.
So, you know, usually I was first worried that young people wouldn't know who they were. but you know, I went to my daughters, they knew who they were. So I figured that I was going through the age range of the people that I would interact with. Thank you.
Yeah, I'm pretty sure my daughter would have no idea who those were. And she's about to be 14. But I don't think she ever saw full stones.
But the real problem was